6 minutes ago, high in the mountains of Chile, a machine with an eye wider than almost any telescope ever built finished another image of the southern sky. That single exposure was not meant to capture one beautiful galaxy or one famous star. It was designed to catch change itself. This is what makes the Vera C. Rubin Observatory so different. It is not simply taking pictures of the universe. It is building a memory of the sky night after night so that the cosmos can no longer change in silence. Constellations seemed fixed, galaxies looked frozen, and the universe felt too vast and too slow to change within a human lifetime. They usually pointed toward one target, gathered as much detail as possible, and moved on. Hubble revealed extraordinary structure. James Webb opened the ancient infrared universe, but Rubin was created for a different purpose. It repeatedly returns to the same enormous regions of sky, photographs them again, and compares every new image with what came before. Anything that appears, vanishes, brightens, dims, or moves becomes part of an alert system designed to respond almost immediately. The heart of the mission is a decade-long survey of the southern sky. Every few nights, Rubin will revisit nearly everything visible from its location and build a constantly updated movie of the universe. Each alert represents a change, perhaps a supernova igniting in a distant galaxy, a near-Earth asteroid changing position, a variable star pulsing, or an object nobody has ever cataloged. The data stream is so large that no team of astronomers could inspect it manually. Automated systems and international data brokers must sort the flood, classify the events, and direct human attention toward the most urgent and unusual discoveries. Even Rubin's earliest observations showed how powerful this approach could become. In a limited set of commissioning images, the observatory captured a staggering field filled with millions of galaxies. Hidden within the early data was a vast stream of stars torn from a galaxy by gravity. The stream stretched farther than the diameter of the Milky Way, a faint river created by a violent interaction that had unfolded over immense spans of time. It had always been there. Humanity simply lacked an instrument with the necessary combination of sensitivity, coverage, and patience to recognize it. That discovery revealed the deeper power of Rubin. A dim arc can become evidence of a galactic collision. A disappearing star can become the signature of a black hole being born. A moving dot can become a dangerous asteroid or a fragment from another planetary system. Rubin's strength comes from context. By observing huge areas repeatedly, it can connect events that would otherwise look unrelated and show astronomers how the universe changes across hours, months, and years. One of the most dramatic early examples came from an asteroid called 2025 MN45. Then astronomers measured its rotation. The object, estimated to be hundreds of meters wide, appeared to complete a full spin in less than 2 minutes. For something so large, that is astonishing. Most asteroids of comparable size are believed to be rubble piles, loose collections of rock and dust held together by weak gravity. Spin a rubble pile too quickly and centrifugal force should overcome that gravity, pulling the object apart and scattering its pieces into space. Yet this asteroid remained intact. That means it may be far stronger and denser than ordinary rubble. One possibility is that it is a solid fragment from the interior of a much larger ancient body. Long ago, during the chaotic formation of the solar system, planetary objects repeatedly collided, shattered, and reassembled. If 2025 MN45 came from the compressed interior of one of those bodies, its strength could allow it to survive a rotation rate that would destroy a loosely bound asteroid. In that case, Rubin did not simply find a fast spinning rock. It may have found a surviving piece of a vanished world, carrying physical evidence from the solar system's most violent era. The object was not alone. Rubin's early asteroid data revealed multiple bodies rotating far faster than expected. It tells scientists about internal structure, composition, collision history, and strength. A slow spin may suggest a loose aggregate. An extreme spin may point towards solid rock, metal-rich material, or an unusual past. By discovering enormous numbers of asteroids, Rubin can turn rare curiosities into statistical populations. Instead of debating whether one object is exceptional, researchers can determine how common these extreme bodies are and what they reveal about the processes that built the planets. The scale of the asteroid search could be revolutionary. Rubin is expected to identify vast numbers of previously unknown objects, including main belt asteroids, distant bodies beyond Neptune, and near-Earth objects. Repeated observations improve orbit calculations, helping scientists determine whether an object poses any future risk. Rubin may also detect small asteroids shortly before they strike Earth's atmosphere. Those objects are usually too faint to see until they are very close. But even a brief warning could allow researchers to aim instruments toward the predicted location and study an impact as it happens. Asteroids are only one part of the changing sky. Some of Rubin's most unsettling discoveries may involve stars that do not explode but disappear. Massive stars are expected to end in brilliant supernovae, blasting their outer layers into space while their cores collapse. Yet theory predicts that some stars may collapse directly into black holes with little or no visible explosion. Detecting one is extraordinarily difficult because astronomers are not searching for a sudden flash. They are searching for an absence, a star visible in earlier images that is no longer there. A repeated survey is perfectly suited to that challenge. Rubin can compare the same galaxy across many nights and flag a star whose brightness drops dramatically or never returns. A possible candidate in the Andromeda Galaxy has already renewed interest in this silent form of stellar death. If such cases are confirmed, they could change estimates of how black holes form and how many exist. They would also show that some of the most important events in the universe are not announced by explosions. Sometimes the clue is that something enormous has quietly stopped shining. Rubin's alert system is built for exactly this kind of mystery. In a single night, it can identify hundreds of thousands or millions of changes. Data brokers around the world will filter the alerts according to scientific interest. One group may search for supernovae, another may focus on asteroids. Others may hunt for rare variable stars, tidal disruption events, or signals that do not fit known categories. The challenge will not be finding change. The challenge will be deciding which changes deserve immediate attention before they fade forever. Supernovae will be especially important because they can be used to study the expansion of the universe. Certain stellar explosions, particularly type Ia supernovae, have predictable brightness properties that allow astronomers to estimate their distances. Measurements of these events helped reveal that cosmic expansion is accelerating, leading to the idea of dark energy. Rubin could discover an enormous number of supernovae, creating a data set far larger than anything previously available. With enough events spread across cosmic history, scientists can test whether dark energy behaves like a constant or changes over time. If dark energy is constant, cosmic expansion may continue accelerating indefinitely. If it evolves, then many assumptions about cosmology may need to be rewritten. Rubin may also help address the Hubble tension, the disagreement between different methods of measuring the universe's expansion rate. A massive, carefully calibrated sample of supernovae could reveal whether the conflict comes from measurement problems or from missing physics. The observatory cannot guarantee an answer, but it can provide the volume and consistency of data needed to make the disagreement much harder to ignore. Rubin may also transform the search for interstellar objects, the rare comets and asteroids that formed around other stars and later wandered into our solar system. These visitors move quickly and follow open trajectories that reveal they are not gravitationally bound to the sun. They are often discovered late, after they have already passed their best observing position. Archived Rubin images showed that the observatory had captured the interstellar comet 3I Atlas before its official discovery elsewhere. That early detection demonstrates why Rubin could become a powerful interstellar object hunter. Because it photographs wide areas repeatedly, it can trace faint objects across multiple nights and reveal their unusual motion. Discovering a visitor earlier gives astronomers time to prepare. Webb can examine its chemistry, Hubble can study its activity, radio observatories can search for molecules. Spacecraft may even observe it from different locations. The next interstellar object may be found far enough in advance for a dedicated mission to consider an interception, turning a brief telescopic encounter into direct exploration of material formed around another star. The number of such visitors remains deeply uncertain. Rubin might find only a few, or it might reveal that interstellar space is filled with wandering debris. Planetary systems naturally eject objects through encounters with giant planets, binary stars, and passing stellar neighbors. Across the galaxy, those processes should produce countless fragments. Most are simply too small and dark to detect. Every new interstellar object would provide a physical sample of another system's formation history delivered by chance into our neighborhood. Rubin could show whether the 3 confirmed visitors seen so far were rare accidents or the first visible members of a much larger population. It is the invisible structure of the universe. Ordinary matter, everything that forms stars, planets, and people, represents only a small portion of the cosmos. Dark matter provides unseen gravity that shapes galaxies and clusters. Dark energy appears to drive accelerating expansion. Neither has been directly explained. The observatory carries the name of Vera Rubin because her measurements of galaxy rotation provided crucial evidence that visible matter alone could not account for the motions astronomers observed. Rubin Observatory will extend that legacy by mapping billions of galaxies and measuring how their light is distorted by intervening mass. This effect, called gravitational lensing, allows scientists to trace matter even when it emits no light. By combining lensing with galaxy positions, redshifts, and supernova distances, researchers can reconstruct the cosmic web across vast stretches of space and time. They can test how structures grew, how dark matter gathered, and how dark energy influenced expansion. The result may become one of the most detailed maps ever made of the universe's invisible skeleton. Early images have already revealed hidden stellar streams, extreme asteroids, possible silent stellar deaths, and previously unnoticed views of interstellar visitors. The full survey will repeat this process night after night for years. Every image will become more valuable when compared with thousands taken before it. Patterns will emerge. Rare events will accumulate. Objects that once seemed unique may become members of entirely new populations. More importantly, the discoveries will not arrive one at a time. They will overlap. A supernova may ignite while an asteroid approaches. A galaxy distorts background light, and an interstellar object races through the same night. Rubin will watch all of it together, giving astronomers something no previous observatory could provide: a connected record of a restless universe. For centuries, astronomy showed us what the universe looked like. Rubin will show us what the universe does. It will catch galaxies being torn apart, stars dying quietly, asteroids racing through darkness, and visitors arriving from distant systems. More importantly, it will record enough of the sky for change itself to become measurable. The universe was never frozen. It was always moving, colliding, fading, erupting, and transforming beyond the limits of our attention. Now, for the first time, we have built an observatory designed to remember yesterday's sky well enough to expose what changed today. And the longer it watches, the harder it becomes to imagine what it might find next.